I'm Augustus Bacigalupi, and this video describes a schematic design for an exhibit done in collaboration with Bob Kentner of the Tech Museum, San Jose. There's a lot of information here, and this is not how the exhibit would actually look. It's really just a series of diagrams to describe how an exhibit might work. The way it's broken up is there's these interactive elements here and here. Let's zoom in on this one for now. But yeah, so there's this dial that would be an actual physical dial, and then there's here's a very schematic diagram of a transistor, and it could be, as Bob suggested, that it could be like LED lights. It could be just on a computer screen and be virtual and then controlled by an actual analog device, dial, or in the case of what I'll call digital, the switch. So here we have a dial that's analog in the sense that as you turn up the voltage, it biases this transistor and allows more current to flow. And so over here, it just sort of schematically shows it, you know, as the dial is turned, this brighter red indicates more voltage, and then this brighter yellow is meant to indicate more current. In the digital case, we have this switch, so it goes from 0 to 5 volts. So at 0 volts, no current flows, and when someone switches an actual physical switch to 5 volts, it causes all the current to flow. If someone was a little older, or a kid was just really interested, or an adult's interested, we could have more information. Bob suggested there could be like a companion video to the exhibit that would go more into detail. So one of the details could be the load line diagram of a transistor, which is common to all transistors. And here we have the current, the collector current, and then the voltage across the collector and the emitter. And these diagrams are really helpful in describing the difference between analog operation and what we call digital operation. So in analog, the majority of the circuit will operate along the linear line itself, and so it'll continuously increase the current as the voltage is increased. Down on this load line diagram, we've highlighted the N, so this is cut off, meaning no current. And then saturation is when we max out the current and totally bias this transistor to allow the maximum amount of current and saturate the transistor. And this would be analogous to a high state or a digital 1, and then this would be analogous to a low state or a digital 0. So now let's move on to the neuron portion of the exhibit. Now here we have some interesting opportunities, because what we can do now is create kind of a game scenario where we've described the analog functionality of a transistor and how it differs from the digital functionality of that same transistor. Now for a neuron, the neurobiology is rather involved. We could loosely think of these action potentials here coming from other neurons as digital switches. These action potentials come to our subject neuron, and this subject neuron in this portion of our exhibit can be, I had a friend suggest that it could be actually built out of resin and then have LED lights inside, or it could just be a virtual neuron on a computer screen. In any case, there would be banks of these switches and banks of these dials, and a number of people would sort of be necessary to get our neuron to then fire. In other words, to have the subject neuron give off an action potential of its own. And this is where the game part comes into the exhibit, and where a lot of fun could be introduced into this learning opportunity. Because what you could have is a bunch of people switching switches, which will send these action potentials from other neurons. And then you can also have these analog dials. And then what these dials would do will change a number of different environmental factors and factors about the neuron itself. For example, while someone's switching these switches, it'll send action potentials down these dendrites here at a certain rate. And then you might have a local field potential, which are the electromagnetic fields surrounding the neuron, any given neuron. And when the frequency of this field is synchronous with the people switching these switches, then the likelihood that the subject neuron will fire will increase. And so it really kind of requires that these people playing with these dials kind of work out with these people switching these switches in order to get this neuron to fire. So that sort of becomes the objective of the game, is to get the neuron to fire. And then, you know, there's always one in every crowd. You know, this dial here could be turned down to actually inhibit firing as a function of neurotransmitters, which a lot of us have, we hear about in popular culture. And then there's ion gates and neurotransmitter receptors. I mean, there's a lot to be learned about neurons. And again, the point of this isn't to give someone a lecture on neuron morphology and functionality, but there is an opportunity to create a game experience out of it. And then if someone's interested in neurotransmitters and how they affect the firing of a neuron, or what local field potential is, then there could be companion videos and other material associated with the exhibit that they can dig deeper into all of these issues. So that covers the basics for now. You know, there's some other ideas in here, but it'd be nice to get some feedback from other folks, see what they think about how this might or might not work. And yeah, we'll see if we can't make it happen. If not for this round of exhibits with the microchip series, maybe it'll be picked up for some other exhibit.